x minus 2 minus x dx.
Yeah.
So take the constant out.
Yep.
Why do they put negatives here?
Because Hooke's law. Have you learned Hooke's law before?
No.
Then I can say something. It's not very difficult, but it's very common. Saying this is the wall, and here is a spring. So I can push it. This is a spring. I can give it a force. And I find that the more force I give, the more displacement it moves, right?
Yeah.
So it's kind of like a force over the displacements dot x. Then I move it here, and so this one is dot x. And they have, as long as it's the same spring, so they're proportional. So that's okay. And also because you can see that the force that I give in here is going to be negative. Yeah, if I give force in here, oh, this one is doing this. If I give it a force in here, let's say I pull it, not push it. If I pull it, so if I give it saying it's negative, give it x. This is saying, let's say this is a 0.5 meter. So negative k times 0.5. This is a positive displacement, right? This is a positive displacement, right? But the direction of the force is in that direction. So they're the opposite. So that's why they write a negative.
Got it.
And also, as long as the same spring, this k is certain. So it's called spring constant. So we
Oh
can
yeah,
say
I know that.
Yeah. Oh, you know that? Yeah.
Like it's like the amount of compression.
Yes, you can feel that this spring is hard to press. That spring is easy to press. What we describe is basically is that spring constant k thing. Does that make sense?
Yeah.
So that's why it's the opposite. So that's why we write the negative there.
Yeah, I'm just gonna finish this up real quick.
Yeah.
Okay, here we go. What is the work by spring as a done by spring? Okay, and then we just have to do that. K minus x. I'm pretty sure you don't have to simplify, do we? Yeah, I'm pretty sure we don't.
Yeah. This is 2, right?
Yeah.
Okay, then it's okay.
Minus x 2. Like that. I forgot k. I'll just put it right there. Yeah, that should be fine.
Yeah. Where's your like x1, x2?
Oh, I didn't see the 1 there. Okay.
Oh,
yeah. Okay. Yeah. So it has x1 and then...
Yeah, you can simplify it by if I substitute 1 over k out. If I get that one out, what's left is minus x1 squared, and this one is, let me see. This is negative. That one is positive. Wait, let me think about this. Minus x1 squared, I get it. If in that case,
yeah, you can just get rid of the negative side. I prefer just to copy it so I don't make a mistake, but yeah.
Yeah. If you substitute, so eventually it's basically 1 over 2k times x squared, right? I get negative 1 over 2k out, so it's negative x1 square minus negative x2 square, right?
Yeah. Just taking
Mm.
out the 1/2. Yeah, I see.
Yeah. I think the sign here is not right, so that's why I'm writing this again. If you, in your
What?
case, it's negative x2 squared, which is I
Yeah,
don't
but
have it.
isn't. Oh, yeah, I forgot the negative part here. Okay, yeah. So that would be. Wait, no, I don't think. Would that change anything? I don't think so, because
No,
isn't it
that is still
just
true.
7?
That's still true anyway. You have to
Yeah.
substitute negative negative x2, negative x1. Yeah, that's okay. What's different between this one and this one? It's in the end it's different, but I don't see why it's different. But I'm sure this one is right. Because I get negative 1 over k out. So what's left, it's kind of easier for me.
I think. Oh, I don't. I think they're the same.
Wait,
Maybe.
because this is negative and negative,
Yeah.
so eventually it's
Oh,
positive, right?
maybe that
Oh yeah,
negative doesn't
that's
have to be there.
yeah. If you don't have that one, that'd be okay.
Yeah. I don't know how that got there, but
Wait.
yeah.
Oh, if you have that one, that's actually okay. Well, you have to have that one. It's the same.
Okay.
If you have this one, which is negative, negative, oh, this one is okay. This is inside. Yeah, then eventually it's the same.
All right. Yeah.
No,
Okay.
no,
Got
okay,
it.
then.
Oops.
There's a second method, which means we can use the graph. If I got the graph, which is like this, I can also just get the area, which is the same result. Is that what you
Oh
mean?
yeah.
Kinetic energy you have learned, right?
All I know is that EK is equal to 1/2 velocity squared and then times mass.
Yeah. It's because in formula number 5, in big 5, in unit acceleration, we have v squared minus v0 squared is equals to
2a.
2a delta x, right?
Yeah.
Because of this, we can actually do something, which means I can use Newton's second law saying A is F over m, right?
Yeah.
So this is time delta x2, and then I time it on both sides, time m, and divide it by 2. So I can say F delta x, and this is 1 over 2 mv squared minus 1 over 2 mv0 squared, which equals to 2 F delta x. Does that make sense?
Yeah.
Yeah, and this is easy to say something in the phenomenon. It's basically because of that force, and I make the initial zero kind of kinetic energy into this, eventually this one, right? So that's why you increase, your kinetic energy increase because I make the work F times delta x. That makes sense?
Yeah.
So that's we describe what is that 1 over 2 mv squared. It's the energy and initially, and this is the energy finally. And that's why we say it m1. This is the definition of kinetic energy, and also proven in a lot of other situations and phenomena. So that's why we keep it there that way. So this is kinetic energy. And what I just wrote basically is the new principle theorem, work energy principle, which means the work you've done, F delta x, equals to delta k, right? Which kinetic energy change of kinetic energy.
Yeah.
Basically what I just did, basically. Does that make sense? So, and I call this work energy theorem. And sometimes they don't, for example, if I push it and then there is a little friction, and maybe there's a little wind, see, they have several forces together. So I have work, saying it's work total, or I can use work net. So anyway, I use total work, right? So the total work is going to change the kinetic energy. Does that make sense?
Oh,
Is it making sense a little? Also, conservation of energy. You know, why you increase is because I do the work. So my work is transformed into your kinetic energy change.
okay. Yeah, I was just wondering if it's always like kinetic energy.
As long it's kinetic energy and the work is always like that. Unless it's supernatural power. Unless
Alright.
there's, yeah. Well, the pioneer of the scientists, they well, a lot of them, they know, they think there is
Yeah,
superpower.
telekinesis.
Supernatural.
Mm-hmm.
And also
So,
all the like a Nobel Prize in physics, there's only one exception, one person, which is different. I know someone from Princeton University, and a physicist, he said he know all the, and they all believe in God, so they believe in supernatural things. So yeah, that's why they, in their own paper, you will see a little bit different than conservation of energy.
that's
They basically saying the
yeah.
wind can't create a car, right? You can't really say the wind blows and get a car, right?
Yeah, it's kind of hard to believe in that.
And then
you're a scientist.
you blow into a universe, which is even more impossible.
Mm-hmm.
Yeah. So basically, it's all working, but you have to be careful. Sometimes in the future, we will learn something more about other energy, and then you have to put other energy too, because other energy may be also changed. So it's a little something. So let's just do this one. 6, using this theorem to do 6.
Okay. Let me see. What is the kinetic energy of a ball? Mass equals with this moving with a speed of 30 meters per second. Yeah, and then use a calculator. Speaking, let me get a calculator.
Sure.
Okay, got it. So 0.05 times 30 squared, 45.
Yeah. And then unit is J, right?
Yeah, 45 joules.
Yeah. And 7.
Tennis balls hit straight upwards with this initial speed of 15 meters per second. How high would it go? Okay, yeah, I got this one.
Yeah. It's better to use the new method that we learned. This one. We can have the old original method to do that too, but we want to use this one.
Work total equals change in kinetic energy. So, change in kinetic energy 50 meters per second from 50 initial to 0. So the work would be that. How do I change that into joules?
I think what you write is basically a diagram. This one is 50. And then eventually it's 0 in here and 50 in here. Right? That's what you meant, right?
Yeah. I know how to do it like, what is it? This way. So times 50 equals mass 0.06 times height times gravity, which is 10.
Yeah. This is
yeah, how do you do it the new way?
This is a kinetic energy, well, mechanical energy conservation, I think, what you're using. So you say, well, So let's say the work total. The work total from here and here, work total is done by only one force, which is gravity, right?
Gravity.
Which
Yeah.
is mg time, if mg is, let's say if mg is positive, and then then this is a negative. So your mg is in here, but my displacement is in here, so it's a negative mg times what's the, well, d we don't really know, right?
Yeah.
Yeah, and that equals to, so this is the total work, right? There's only one force, right?
Mhm.
And then it's 1/2, basically is key final minus key initial.
Oh, I thought. Okay, so that K right there is kinetic energy, not just velocity. Okay, got it.
Oh yeah, no, oh no, velocity. Oh yeah. Oh, before we think velocity is everything, but math also is something, right? When you talk about
Mhm.
energy, about moving objects. So 1/2 mv, which is 0 square in the end, right? Minus 1/2 m, which is 50 square. You know what I mean? So that's why
Okay,
I
yeah,
want
that
to.
makes a lot more sense. So that would be, yeah, and that comes back to what I was basically doing, but now with this rule. So negative 0.5. Oh no, they have both. They both have a negative. So
Yeah,
we can get
so
rid
they
of this,
cancel. Yes,
this, and this. So
basically what you
0.5.
wrote. Then it's how it's deduced in this like theorem.
Yeah, that's good to remember. Tennis, yeah. We can move on from that one.
Yeah, so this delta K is kinetic energy final minus kinetic energy initial. Delta K sometimes is confusing. We use big five, also can prove that, but let's use the new one. Because in the future, some of them is not easy to do done by big five, but easier done by energy and work. 8. Oh, we need the example 4. You can read this and then we'll go back to the example 4.
Okay. I could just take a screenshot of that.
Oh, you can take a screenshot of this and then
Yeah, and then you can
example
go back to 4.
4. Oh, this is 4. Oh, that big one.
Give me a quick second. Let me just place that screenshot somewhere. Oh man, time flies.
Yeah.
I just find a document. This should be good. Okay, consider the box sliding down an inclined ramp in example 4. If it starts from rest at the top, what speed does it reach at the bottom? Okay, so work
Total?
which is work total.
That's the right work total because before later we'll find several work together. Yeah.
Work total. It's asking for what is the speed. Okay. Work total is just gravity.
Actually, work total you have done there in that question. Just the question.
Oh yeah, I
B.
kind of forgot the answer though.
Yeah, let's just say, let me just write. Because the first one is mg sine theta times 8. And the second one is 0. Oh, times 8. This is times 8. And the second one is 0 and minus that because this one is negatives. and mu mg cos theta times 8. So this all together equals to,
You can also say like,
change, oh, we don't have to do it because it's exactly the same question. Let's just use this number.
yeah,
1008 joule.
one. I can't see right now.
1008.
Okay.
Yeah, let's just use it in here and in here. Because the left
So
is 1008 J equals to,
initially it's just 0. So
yeah,
actually, is it?
yeah. This one start
Okay,
at
yeah.
rest, yes.
1, 2 mass velocity squared. It's 35 kilograms.
Yeah,
So yeah, let me just use the calculator here.
yeah.
So 8 times 2 divided by 35.
Yes.
And then square root that.
Yeah.
So 0.2 something.
Ooh.
39.
It's 2 times
Oh wait, yeah.
1008. You probably use 1.008, right?
1.00. Yeah, it's 1.008 times 2.
No, it's not
And
1
the-
point. It's 1008.
Oh.
Huh.
Okay, yeah. So then
It's
2000, yeah.
2 times 1008 over 35, right? And square root of it.
Screw root that. 7.58.
Yeah. So now we can think about this. Is it making sense? Making sense is extremely important in physics. So it's just something is doing the work, which is gravity, right? For the slide. And then eventually increase its kinetic energy, right? Does that make sense? Gravity is the reason why they make this motion, right? Does that make sense? So
Wait, can you
gravity-
say that again?
So this
Yeah.
basically, this indicates gravity, mg, is doing some work. So eventually this doing work increase the kinetic energy.
Mm-hmm.
This is what they describe, basically, the phenomenon. So which means we slide. When we do the slide or ski, a lot of time is the gravity is helping us, right? Including your swimming, right? When you jump into the water, the gravity also does some of the work, right? Actually, after you first make the move, all the things until you get the water is done by gravity.
Yeah, 1,000 free fall.
Yeah, and then you have to make the work by yourself by swimming, right?
Yeah.
And then gravity is gonna be canceled by what? By the water. They give you some force, and you still have to do something.
Yeah, definitely.
Okay. So next one. Oh, here. 9.
Pool cue. Striking a stationary billiard ball. Mass equals 25 gives the ball speed of 2 meters per second. The average force of the cue was. I'm assuming it's just gonna be there for. So basically it's saying 200 times what?
Yeah.
Times what equals 1/2 times 0.25.
Yeah.
4.
So this is also the theorem, right?
Mm-hmm.
Yeah. Then you can find it. I don't think we
Mhm.
can find it. The calculation eventually is this 0.25 centimeter. And we also make a very short estimation whether it's making sense. Which means that 0.1 centimeter is short, right? 0 point is a quarter of centimeter, which is making sense in the pool playing, right?
Yeah.
Mhm.
Oh yeah, and also you had to convert from meters to centimeters.
Yeah. This is also by estimation because physics also make a lot of mistakes, so it's better use estimation a lot.
Mm-hmm.
And the rest of it is going to be gravitational potential energy, which you learn, right? MGH, right? Or negative MGH, basically. Have you learned negative MGH?
Yeah, gravitational energy equals that.
Yeah,
I know like all of them, like
if you
elastic
know,
energy.
you can try to do a little bit more. So the homework
Yeah.
is just review all the questions that we did,
And also, yeah, find out this all that science stuff. Do the practice problems more. Yeah.
yeah, and well, the rest of it is not that difficult unless you reach here. You probably can stop. This is a little tricky
Oh
to
yeah.
explain. Yeah,
Mhm.
until here, until 16, you probably can done it. And there
Okay,
is
yeah.
only one theorem, but it's also better be remembered it's negative MGH, which is the negative MGH is the
Is it always negative NVH?
yes, it's because this one, yeah, for example, if I have this is the ground and this is 10 meter as my height. So what do you think is the if I move this, if I have my hand, I move this stone in this level, and then I can say what? Because it's against that. It's against the work because your gravity is in here. So your potential energy is negative mg times 10. Does that make sense?
Yeah.
Mm.
Got it.
So you can do from at least from do to example
16.
9. And
Oh.
if you do not like the new part, if you like the new part, you can do until 16.
Yeah, I'll try my best to get to 16.
Or you can just stop at 9, which is all in one that will finish. Okay.
Yeah. Mm-hmm.
And the rest of it, there is only one theorem. Other than negative MGH, negative MGH is also because of this. We also love one other formula that didn't really say in this time is mg times delta h. That makes more sense why it's negative. Because you're dropping it from 10 meter to 0 meter.
Yeah. Oh yeah, that does make a lot of sense because
you lose some
especially-
energy, right?
especially when you're like working with the change in work, right? So
Yes. So it's because it's 0 minus 10. So that's why it's negative. Yeah. So that's why instead of MGH, we write negative MGH or we write mg delta h. And there is just the conservation. I think you probably learn conservation of energy or mechanical
Yeah.
energy here, right? This one you learn, right?
Yeah, that's like the basis for our pretty much our whole class.
Yeah. Okay, sure. Then that's it. Do you have other questions?
No, I think I'm good. And
Okay, let me know if you can send it to the
yeah,
group.
one slight question.
Yep.
The sine problem, like which one is sine and cosine? I think I could figure that out. Like clarify it on my own. So yeah, I think I'm good.
Yeah, example 4. That's yeah.
Mm-hmm. Well, yeah, thank you.
Yeah,
See you.
thank you. God bless you.
Bye.
Bye.